Hello, this video is entitled Basic Integration Rules. Now this name might be a little deceiving, but what this section, and not every book will have a section like this, it's essentially a summary of various integration techniques that we've already learned. This is a new chapter in this book. It's chapter 8. And then before we move into some of the more advanced techniques, however, there are two new integration techniques that we will learn in this section. Everything else would have been previous types of integrals forms learned. Like looking at some of these, this one fits right into arctan. I just picked some examples to show you. And this one, if you do a substitution, you're going to end up with a natural log. This one would require division before integration and would most likely have arctan after you divided. Remember, an improper fraction is if the larger power on top is greater than or equal to on bottom integer exponents. That doesn't count for radicals. You have to divide first before you can integrate. The bottom left is an arcsine form. This next one would be U substitution, and it would not be natural log like this one above it. The reason why this one's natural log is because that's to the first power in the denominator, meaning -1 when you bring it up. Any other power other than -1 is going to be using, the power rule, which is the, n plus 1 over n plus 1 rule. And then this type of integral is something that we will encounter later in this chapter. Now this is one of the two new things we're going to see in this particular section. And then I have some problems selected in here that were from kind of review problems. We'll take a look at those too. But this one, it's called a disguised form of the log rule. Meaning that, so let's take a look at this integral. 2 divided by 7e to the x plus 4. Now, if we had an e to the x in the numerator, it would just be regular substitution. We would let u be the denominator, and then the derivative would give us that e to the x on top. But we do not have that. And this is called the disguised form because we're going to do something to it that's going to make it work that way. It's just not in that form right now. Let's take a look here. So what you have to do is the coefficient doesn't matter here. You can't pull out the coefficient because of this plus 4 right here. I've seen people make that mistake from time to time. But no, just leave it there. And you look at whether this is e to the x or e to the negative x. If it's e to the x, that means we're multiplying top and bottom of our integral then by e to the negative x. You're multiplying it by the opposite. So once you know to use this technique, it's not difficult to use. It's just remembering how to do it. If you just blanked out and didn't study it, then it could throw you off. But as far as actually doing it, it's not difficult. Because you multiply top and bottom by e to the negative x. See, I pulled the 2 out. I could have left the 2, pulled the 2. Didn't matter. Either way, I have e to the negative x on top. Now here, when you multiply e to the negative x times e to the positive x, they actually cancel out to 1. Like right here. One way you can look at it is if you add the exponents, you're going to get e to the 0. Or if you write e to the negative x and make it division, you have e to the x over e to the x, which would still be 1. So either way, it's going to be 1. So it cancels out the e to the x, and then it brings in an e to the minus x right here. So it creates 2e to the minus x's. Now, that enables us to use regular substitution. So we could not let u be the denominator as it was in the original integral. But now we can. Because if we let u equal 7 plus 4e to the negative x, don't forget the derivative e to the negative x is negative e to the negative x because the derivative of the exponent is -1. So I have negative 4e to the negative x dx. Multiply top and bottom, or divide by -4 on both sides, so it gives you -1/4 du. So negative 1/4 du takes care of that e to the negative x right there. Which, of course, I can leave the du right here, and then I can bring the negative 1/4 out with that too. And then the entire denominator is just u. So now you have du over u, and then this will combine into negative 1/2. Well, du over u to the first power, that's a t, first power, is automatically natural log of u. So it's negative 1/2 natural log of u, and then it's negative 1/2 natural log of 7 plus 4e to the negative x, absolute value of that, plus c. So that's the whole idea of this being the disguised form, is because it was not a logarithm in its first step, but then it turned out to be after we multiplied top and bottom by the opposite. Well, let's take a look at this next example. Notice we have an e to the negative x here this time. So that means we're going to multiply top and bottom by the opposite of that, which is e to the positive x. So we're always multiplying top and bottom by the opposite x sign of the exponent. So the e to the x times e to the negative x will just turn into 1, and now the 5, which I pulled the 5 out or whatever, like that's fine if you don't. But either way, you get an e to the x on top, and then now an e to the x goes with that 3, and then a 1 here. And then once you have this form, it's pretty straightforward. Just let u equal 3 to the x plus 1, 3e to the x plus 1. And then the derivative then will be 3e to the x dx. So it's 1/3 du equals e to the x dx. And then, so we have a 5 from that numerator with a 1/3. Now it's du over u. So it's 5/3 natural log of 3e to the x plus 1, then plus c. So that is essentially the one new rule here. The first is the number 2. The second one is these kind of problems using a conjugate technique to integrate trig functions. Now, sometimes trig functions can be interesting and challenging because you can sort of approach them from several different ways. Now, this one probably doesn't. You kind of need to sort of approach it this way. But there are some where it can have multi-approach there. So, okay, conjugate, like x minus y, x plus y. We use conjugates, back in finding imaginary solutions and things like that. And so all you do with conjugate means you just change the sign between the two terms. So I have 1 minus cos of x, so I multiply top and bottom by 1 plus cos of x. And that will give me 1 plus cos of x on top, and then 1 minus cos squared of x on the bottom. So here's where it becomes important to use the appropriate trig identity to help us complete our integral. That's not going to help us much with 1 minus cos squared. But as soon as we realize that 1 minus cos squared is sine squared, then we have something. So we have 1 plus cos of x over sine x, squared x. Now, it's often common when you have several terms, 2 or more terms on top and 1 on bottom. Usually, I say usually, I never want to say 100% on anything. But when I say usually, it's well over 90% of the time. You would split these into 2 pieces. So I'd write this as 1 over sine squared and then cos over sine squared. Now 1 over sine squared, we convert to cosecant squared using the trig identity. And cos over sine squared is a pretty easy u substitution. You can let u be sine of x, and then du is cos of x. So you'd have u to the negative 2 du. Now for cosecant squared, there really isn't a technique to apply here. You just kind of have to know that since the derivative of cotangent x equals negative cosecant squared, that means cosecant squared integral will be negative cotangent. So you kind of just have to know that one. Whereas this one, you're applying, the power rule here. So it's u to the negative 2 makes it negative u to the negative 1. And so you have negative cotangent of x minus sine of x all raised to the negative 1. Notice that's not inverse function. That's probably why I'm using parentheses. That to me, that's perfectly acceptable. If somebody wrote that on a test that way, that's fine. But, you might see it converted to this. So it doesn't make this flag, doesn't mean this answer's more right than the other one. It's just written different because sine of x and negative 1 is 1 over sine, which is cosecant. So they're both correct. They're both equivalent answers. Alright, so there's an example of that conjugate problem. Now here's a problem that I showed that can be done without conjugates, and actually was this one was much easier to do without conjugates. If you split it up as two fractions, 1 over sine is cosecant, cosine over sine is cotangent, and those have already, integral forms, as you can see right there. There's the antiderivative of cosecant. It's negative natural log of cosecant plus cotangent, and then the antiderivative of cotangent is natural log of sine. So that's basically the answer. Now, had I done this with conjugates, it would have looked like this. I would have taken top and bottom, multiplied it by the opposite, which is 1 minus cosine of alpha. I would have gotten 1 minus cos squared. Oh, it looks like I magically changed the variable to x, didn't I? Well, I should have left it as alpha. As you can see, I wrote it back in alpha in the answer. Maybe I'll have to fix that one of these days, but that's all right. Pretend like it says alpha. And then 1 minus cos squared is sine squared. So sine squared over sine would cancel out the sine on bottom, leave a sine on top, over 1 minus cosine. Now, you wouldn't want to conjugate it again, because actually you're in perfect u substitution form. So u is 1 minus cos x, and the derivative of that sine of x. So you essentially just have du over u, which produces natural log of the absolute value of u plus c. So you have natural log of absolute value of 1 minus cosine of alpha. Now you're probably looking at this, and you're comparing it to that one, and you're going, okay, you're thinking I messed something up here. What did I do wrong? Well, that's the interesting thing about trig, and this also problem incorporates log properties. Log properties and trig properties can make things really interesting. These answers are both right. They're different looking, but they're both right. And I'm not going to go through this process. I'll leave this sitting up here. Of course, you can obviously pause the video. And obviously on an exam, no matter which way you did it, it should be considered correct either way. But I just went through this process and involving natural log properties, and then it's natural subtraction. I put the subtraction at the end, therefore that turned it into division like this, and then did a bunch of stuff here. So I turned that larger answer into that smaller answer, just for the heck of it. Because I didn't know if you would sort of look at that and go, hey, wait a minute there, you got two different answers. But I didn't. I got two different looking answers. So that's part of the fun with trig and identities and how they all relate, kind of interrelate with each other. Then I put it in maple, and I guess it got some sort of answer that was even a little bit different than the other two I got. So it even did a little bit differently, I think. So just to make it even more confusing. Yeah, it doesn't have the minus here and has a plus there, but I think I worked this out, or maybe I didn't to show it was the same. I mean, I'm sure that answer, could also be shown. It reduces to this. So, I see what I did. I used the property where this is addition. In other words, natural log of a plus natural log of b is the natural log of a times b. So I took the sign and distributed it through the parentheses, and then cosecant times sine is 1. Cotangent times sine is cosine. So, yeah, it was also, so Maple gave a different answer, which was also correct. Isn't that fun? Here's one with a secant. Secant x minus 1 on bottom, so the conjugate of that will be secant x plus 1. There we go, like so. So obviously they'll leave a secant x plus 1 on top. Now, once again, identities come into play here, because if you multiply that out, since they're conjugates, you know, like x minus y times x plus y is always x squared minus y squared. So essentially you have sec squared minus 1 right here, and that equals tan squared. So that's very important that turns into one term on the bottom. And then like this other problem, a couple problems ago that I did, we split them up. Sec over tan squared, 1 over tan squared. Now this one's a little bit tricky, you know, until, well, actually later on in this same chapter when we talk about integrating trig functions, this might not have been an obvious step here, but what has to happen here is you have to convert these to sines and cosines, which we'll talk about later. So this actually would make more sense later on. That's one of the steps involving integrating secants and tangents. You know, if it fits certain criteria, and then if it doesn't, you look to convert it to sine and cosine. That's exactly what happens here. All right, so 1 over tan squared is cotangent squared. And then these fractions right here, flip it up, you know, invert and multiply or reduce, you end up with cosine over sine squared. That's going to be an easy U substitution, but let's think about what's going to happen with cotangent squared. And it works like tan squared. Cotangent squared, tan squared would have to be converted to sec squared minus 1 because sec squared has a natural antiderivative, meaning sec squared has the antiderivative of being tangent. So then you can integrate it. Same thing with cotangent squared. If you write it as cosecant squared minus 1, cosecant squared has a natural antiderivative of negative cotangent. And of course, the antiderivative of 1 is x. And this is, just do a u du right here. We've done this before already. And you get negative 1 over sine of x, which, you know, I put a flag there, meaning that's perfectly correct. Of course, if you're checking it against another answer, you know, negative 1 over sine, most likely you're going to see it as negative cosecant. But the first answer is correct. Let's talk about something that Stewie says here, and this will also come up in one of the trig integration section a little bit later, which won't be, you know, a couple sections after this one. And that kind of goes back to this up here where I had 1 over tan squared, and that's going to be true all the time. You never integrate a constant divided by a trig function. You always convert it to its reciprocal function. I've seen students take, like, for example, you know, like this, 1 over sine, and they want to call that natural log. That is not correct. If it was cosine over sine, it would be natural log because you would have the du would be in the numerator. But you just automatically convert those to their reciprocal function. So 1 over sine, you would then convert to cosecant, and then worry about how you integrate cosecant. But you never integrate a number over a trig function. So as you can tell, Stewie looks pretty serious about that. I would listen to what he says. This integral is a little bit weird, but it turns out it's easy, but it looks complicated. And this, now the rest of, oh, by the way, the rest of the problems, unless, let me just check, unless another new technique comes up here, but let me just look real quick. I may not do every one of these. I'll leave them on the screen so you can look at them, but just to save time. Yeah, this is a little bit too much here, but now the rest of these are basically techniques already learned prior to this section, so there won't be So the only two new things were the disguised form of the log rule and conjugating trig functions whenever you think that's appropriate. Now this is a little bit tricky. Choosing the U is difficult here. You got a lot of stuff going on there. And it looks like they're not going to relate to each other. But remember, that's what, erasers are for. That's what, we're not, we don't have to do this right the first time. You can sit there, try something. If you don't like it, go try something else. Well, this one, if you let U be natural log cosine of x, the derivative of natural log is always the derivative of what's on the inside over what's on the inside. So the derivative of cosine is negative sine. The derivative, over cosine, which that becomes negative tan x dx, and that gets your tan on the outside. Of course, it's only off by a negative, but big deal. That still worked out beautifully. So all this complicated looking mess after you pull the negative to the outside means all you're left with is the negative of u du. So wow, that turned out to be quite simple. Not too much effort if you can get it to that part. And of course, u is u to the first. So using power rule. So, u to the 1 plus 1 over 1 plus 1. So it's negative 1/2 u squared. So it's negative 1/2 natural log of cosine of x, all that squared. One thing I want to remind you of is, you cannot bring the 2 down. Sometimes with logarithms, like if you have the natural log of x squared, you can bring the 2 down. But whenever the natural log is raised to a power, you cannot bring that power down. Only when the argument. Let me see if I can sort of write something sloppy looking here. So anytime if you saw something written like this, without parentheses, you would assume that then that's the natural log of x squared, meaning you could bring the 2 down. If that was intended for the natural log to be squared, they would either have to put the 2 above the n or parentheses like that. And then the 2 would not come down. All right, so that's a good quick, log refresher. Never hurts to learn that. Now the next one's pretty straightforward. Now anytime that, of course, one example of where that what I'm about to say does not apply is the disguised form of the log rule. But anyway, when you are looking at an integral involving e, the kind of the first thing you want to look for is, is u going to be the exponent? So obviously that did not apply with that disguised form of the log rule, but it does here. So if you let u be cotangent x, the derivative is negative cosecant squared dx. And you just have to adjust for the negative, so then it's perfect. You've got it set up perfectly. Then it becomes the negative of e to the u du, and e to the u antiderivative is about as simple as you can get because you don't have to do 1 plus 1 over 1 plus 1 or anything like that. Antiderivative of e to the u is just e to the u. So it's negative e to the u in this case, so it would be negative e to the cotangent of x plus c. Actually, this the way I did this problem, this is a definite integral, of course. I don't know, you might would want to split it up. You could certainly split it up, but I just happen to see that, hey, if I let u be 1 minus ln of x, that would create the 1 over x right here. I basically, rewrote that x on bottom as 1 over x to the outside. So if you don't see that, you could still split it up and do it that way. And then the derivative is negative 1 over x dx, so all you have to do is adjust for the negative sign. And then I like changing the limits of integration. So if I put e in here, ln of e is 1, 1 minus 1 is 0. And you put 1 in here, ln of 1 is 0, so 1 minus 0 would be 1. So your integral, and that way we never have to go back to x again. So I have a negative, I have 1 on bottom, 0 on top. Now this next step right here is not a step that you absolutely have to do, but over here in the green, I'm bringing back a property from Cal 1 that shows you if you reverse the limits of integration, you create a negative sign. So what I do here by reversing the limits of integration, I create a negative which will then kill that negative that's already sitting there. So negative will take out negative. And now I have 0 to 1 u du, which is 1/2 u squared. Put in 1, put in 0, and you'll get 1/2 as a result of that definite integral. Now here's another one where u would be the exponent. Sometimes that's kind of tricky to see how that's going to develop into that t squared. So what I'll do often, you don't have to, but I'll do is I'll rewrite it like this. So the 1 over t is t to the negative 1, and then the t to the negative 2, t on 2 on bottom, I bring it up as t to the negative 2. And then if you let u be t to the negative 1, meaning that exponent, the derivative will be negative t to the negative 2 dt. And then it fits perfectly. Well, except for the negative, which you can adjust easily, but that gets you this part right here. So actually, then the derivative of that exponent does give you that t squared on bottom. Bring the negative out. So then it just turns out being the negative of e to the u du. So it makes it negative e to the 1 over t plus c, or you can leave it the way I changed it. Negative e to the t to the negative 1 would also be correct, plus c. All right, this is a completing the square problem that we had in the first part of the course, when we had integrals that were turning into arcsine and arctan and all that stuff. So first thing I did was rearrange the terms, and I pulled out the negative, because when I complete the square, I just want to have x squared by itself. I don't want to have any kind of coefficient, positive, negative anything, or any kind of number. Just want 1x squared right there. So be careful when you pull the negative that we change the sign right here, so it becomes negative 10x. So we've done these kind of problems before, so I'll go through this kind of quickly. So add 25, and remember whenever it was a minus in front of it, if you add it here, you have to add here. If there's not a minus in front of it, you would add and then subtract. So that would be back in the section on the integration of inverse trig functions. So I rearranged the terms and wrote it as a square, 25 minus x minus 5 squared. And then like this, and it fits perfectly into arcsine at that point. So a would be 5, and u would be x minus 5. So the 6 was this constant there, 6. Arcsine of u, which is x minus 5, divided by a, which is 5, plus c. All right, so here's another one. Basically the same thing, so I'm not going to spend much time on this one. Once again, I had to go add because of the minus. It ends up being arcsine. Yeah, so this is basically the same thing as the last problem in the way you do it. So I'm not going to worry about it. So now it's up there, so if you want to pause it and look at it, you can clearly see it. So another arcsine. Okay, this one's a completing the square, but this is the other form, where it turns out being arctan. You know, the difference is obviously that arctans are going to not have square roots there. Arcsine would have a square root. So this one I don't have to pull a negative out because there's not a negative in front of the x squared. So I just take x squared minus 4x. I add 4 and then I subtract 4 at the same time to keep it balanced. So this was not, so it's add whenever there's a negative pulled out. It's add, subtract otherwise. So it's x minus 2 squared plus 5. And then a would be the square root of 5, and u would be x minus 2. Du is dx. So then we have 1 over a. See, there's the formula right there. 1 over a, 1 over the square root of 5. Arctan of x minus 2 divided by the square root of 5 plus c. Now, I'm not picky about having to rationalize these denominators. Maybe your instructor is. Hopefully not. But I have no problem with those radicals sitting there on the bottom like that. Now, another one kind of back from that same inverse trig section integration. Okay, you look at this and go, I can't let u be what's here because the derivative of x to the 8th is x to the 7th. So I need u to be something that when I take its derivative, it's going to have an exponent of 3. Therefore, u would have to have an exponent of 4. Because that way, when you take the derivative, it will subtract 1, right? So if u equals x to the 4th, du will be 4x cubed dx. And that makes it 1/4 du equals x cubed dx. And then there, everything fits out nicely. So then you have, so a is root 7. So now you just end up with 1/4 du over the square root of 7 minus u squared. So the 1/4, this formula does not have the 1 over a like arctan does, but it's the 1/4 from the du, arc sine of x to the 4th over root 7. I just put this problem maple for the heck of it. So maple they actually rationalize that denominator. Well, good for them. I guess it was programmed to do that. I don't personally care. Here's another one, basically the same idea, but it's plus this time. So the difference is it uses a different formula that we learned in the section on hyperbolic functions. This is one of those ones we learned. So you see when it's plus, then it's going to have this formula. So that's the only difference. I won't go through everything there because the rest of it's the same. But this is the integration formula that I'm using. So how about this one? Now, actually, just to let you know, if the sign was not squared here, if it was just 4 plus sine of x, I would let u be the denominator, and then that would give me du on top. And then that answer would be a natural log. But you can't in this case. You got to let u be sine to get cosine as your derivative. Then you just square the u to make it sine squared. So u has to be sine by itself, du is cosine, and u squared will be sine squared. And then it turns out easy. So it's du over 4 plus u squared. It's the arctan, so a is 2, square root of 4. 1 over a is 1/2. Arctan of u over a, sine of x over 2, plus c. And that concludes this video on basic integration rules.